Welcome back to the Deep Dive. Ready for another deep dive? Today we're taking a look at Physics of Language Models, Part 1, Context-Free Grammar. It was published on May 24, 2023 by Zeyuan Allen-Zhu and Yuanzhi Li. Considering your expertise in machine learning, I think you'll find this deep dive particularly interesting. At its core, this paper explores how language models learn the intricate structures of language, especially those defined by context-free grammars, or CFGs.
CFGs have their foundations in formal language theory, offering a structured way to both generate and analyze strings. And, they actually hold a special significance for us in natural language processing because they can effectively represent the hierarchical structure of sentences.
The paper presents a pretty fascinating finding. Even pre-trained transformers can achieve almost perfect accuracy when generating sentences from CFGs, even those that are potentially ambiguous.
And they don't just stop at accuracy. The paper shows that these models achieve an impressive level of diversity in their output, which tells us they're not simply memorizing a handful of set phrases.
To test this rigorously, the researchers chose to use a pre-trained GPT-2 model.
Yes, and they created a set of 5 synthetic CFGs, each with varying levels of difficulty. They labeled these as CFG-3BFGs.
Now, using synthetic CFGs is pretty clever, right?
Oh, absolutely. These synthetic CFGs gave the researchers a way to conduct controlled experiments, which are really crucial for isolating and studying the specific capabilities of the language model when it comes to learning CFGs.
Before we dive into the results, could you give us a quick breakdown of what CFGs are and what makes them so challenging for language models?
Sure. CFGs are essentially built on a foundation of rules and symbols. So you have what we call terminal symbols, and these represent the actual words that make up a sentence. And then you have non-terminal symbols, which are more like placeholders for groups of words. Now, the magic happens when you use production rules to expand these non-terminal symbols. And this expansion can happen recursively, ultimately leading to a string of terminal symbols, which gives you your final sentence.
Oh, wait, that makes sense.
But the real challenge for language models lies in the need for long-range planning, especially when they're trying to generate grammatically correct sentences, particularly lengthy ones. Unlike simpler models that might only focus on local token consistency, these models need a global awareness of the entire sentence structure that's dictated by the CFG.
So it's like they can't just focus on what word should come next.
Exactly. They have to understand the whole picture. You see, in the paper, they use this example of balanced parentheses, which is defined by the CFG S minus SS. Now, to generate a string of correctly balanced parentheses, the model really needs to keep track of the number and type of parentheses to ensure that the final string is actually valid.
That makes a lot of sense. It's not just about what's immediately next, it's about the overall structure.
Exactly. And just when you thought it couldn't get more complex, there's another layer. CFGs can be ambiguous, meaning a sequence of tokens can have several valid parent non-terminal symbols within the CFG tree. And this ambiguity, well, it makes it even more challenging for the model to figure out the correct hierarchical structure of the sentence.
Gotcha. So it's like having multiple potential paths, and the model needs to figure out the right one.
Exactly.
So let's get to the results. The paper presents some pretty impressive findings, right? Can you walk us through them?
Absolutely. The GPT-2 model they used actually managed to achieve near-perfect accuracy in generating grammatically correct sentences based on these synthetic CFGs.
That's pretty remarkable.
It is, but in research like this, accuracy alone doesn't tell the whole story. It was super important to figure out if the model was truly understanding the CFG rules or if it was just memorizing a limited set of strings. So to address this, the researchers went a step further and used entropy estimation. This helped them assess the diversity of the generated string and ensure that the model wasn't just replicating a bunch of memorized sequences.
So they were making sure the model was actually learning, not just parroting back what it had seen.
Precisely. And they even went as far as using the birthday paradox with a huge sample size of 20,000 generated strings. This was just to further solidify the diversity of the model's output.
They really wanted to be sure.
Oh, absolutely. And as if that wasn't enough, they also calculated the KL divergence between the model's output distribution and the true distribution of the CFG. And this, well, it showed the model's ability to capture the subtle nuances of the underlying grammatical rules.
So they went above and beyond just showing that the model could generate grammatically correct sentences.
Exactly. They wanted to prove that it wasn't just memorizing, but actually understanding the underlying rules.
And what did they find? Was the model really understanding the rules?
The results were pretty definitive. It wasn't just memorizing, it was generating a diverse range of valid strings, which really indicated that it had grasped the underlying rules of the CFGs. In fact, the researchers argue that this level of understanding is actually comparable to human comprehension of complex grammars. They found that the model could differentiate between valid and invalid strings, according to the CFG, with an accuracy rate exceeding 99%, and this held true across all the CFGs they tested.
Wow, that's really impressive. So we've established that the model can generate these grammatically correct sentences, and it's not just memorizing them. But the big question is, how does it actually learn these complex structures? That's where the physics of learning comes in, right?
Exactly, and that's a topic for our next deep dive.
So we ended on a bit of a cliffhanger last time. How does the model actually learn these complex CFG structures? The paper suggests some potential mechanisms, right?
That's right. To get to the bottom of how the model might be achieving this level of understanding, the researchers used a technique called linear probing, which allows them to take a peek into the hidden states of the transformer, essentially extracting information that's encoded within the model as its processing language.
So they're kind of trying to decode the model's internal representations, a bit like looking for clues in its thought process, right?
Precisely. And what they found is really quite fascinating. Their findings showed that the model implicitly encodes information about the non-terminal ancestor symbols and their boundaries for each token it generates. This means the model isn't just processing tokens in isolation.
Right. It's like it's building a mental map.
Exactly. It's building a representation of the entire hierarchical structure of the sentence as it's being generated.
That's amazing. It's almost as if the model is constructing a mental image of the whole sentence structure, like keeping track of those different levels of non-terminals.
And this observation led the researchers to propose a very intriguing connection to dynamic programming. They noticed that the model's attention patterns had a strong bias towards attending to the most adjacent non-terminal boundaries.
Interesting.
And this behavior, well, it bears a striking resemblance to how dynamic programming algorithms work, breaking down problems into smaller overlapping subproblems and building solutions from the bottom up.
So you're saying the model might be implicitly using a dynamic programming-like approach to handle the complexity of CFG generation. That's quite a revelation.
It is. Now, the paper goes on to explore some extensions to this basic CFG framework. They wanted to see if the model's capabilities could stretch beyond these simple grammars.
Makes sense, pushing the boundaries a bit. So what did they find?
Well, one of the extensions they looked at was this concept of implicit CFGs.
Implicit CFGs, what are those?
In implicit CFGs, terminal symbols don't represent individual words anymore. Instead, they represent categories of words.
So it's a higher level of abstraction.
Precisely. This allows the model to learn more abstract and nuanced linguistic structures.
Can you give us an example of how these implicit CFGs work in practice?
Sure. So they experimented with an implicit CFG where the terminal symbols actually represented different parts of speech, like nouns, verbs, adjectives, and so on. This meant that the model had to learn how to group words into these categories and then use those categories to generate sentences. It's a demonstration of a much deeper understanding of language structure.
That's really cool. It suggests the model is capable of handling a level of abstraction that goes beyond just memorizing specific sequences of words.
Absolutely. But they didn't stop there. They also wanted to know how robust these models are, particularly in handling real-world data that might not always be perfectly grammatical.
That's a really important point, and the real-world data is rarely perfect.
Exactly. So to test robustness, they introduced controlled corruption into the input prefixes. They were essentially simulating situations where data might be incomplete or have errors. And then they looked at how well the model could still generate valid completions that followed the rules of the CFG.
Okay, so they're deliberately messing things up a bit to see if the model can still make sense of it.
You got it. And what they found is that while the model pre-trained solely on grammatically correct data did show some level of robustness, its performance got significantly better when it was trained on a mix of clean and perturbed data. They call this robust pre-training.
So exposing the model to a bit of bad data during training actually helped it to handle imperfect data later on. That's kind of counterintuitive.
It is, but the results are clear. What's even more surprising is that this robust pre-training didn't need a huge amount of corrupted data. They found that even training on a small fraction, around 10%, was enough to significantly boost the model's robustness.
That's pretty remarkable. A little bit of bad data goes a long way.
It does. The researchers suggest that this robust pre-training helps the model develop a more nuanced understanding of the grammatical rules. It's not just memorizing the right sequences, it's learning to distinguish between structures that are intentionally grammatical and those that are just random errors.
It's like learning from your mistakes. Making a few errors during training actually helps you recognize and avoid making the same mistakes later.
Exactly. They observed this fascinating phenomenon that they call mode switching. The model seemed to be capable of switching between different modes of operation depending on the input it was given. So when it gets a clean, grammatically correct input, it operates in a mode that strictly follows the CFG rules. But when it's hit with a corrupted input, it switches to a more flexible mode, trying to correct those errors and generate a valid completion.
Wow, that's really interesting. It implies that the model isn't just blindly following the rules. It actually has a sense of when those rules might need to be bent or broken to make sense of the input.
Precisely. And this ability to tell the difference between intentional and unintentional grammatical mistakes is further supported by how the model behaves when it generates completions using lower temperatures.
Lower temperatures.
Yes, when you lower the temperature during generation, we're essentially encouraging the model to choose the more probable tokens, reducing randomness, and making it more likely to stick to the grammatical rules it's learned.
Ah, I see. So lowering the temperature makes the model more cautious, less likely to deviate from what it thinks is the right path.
Exactly. And when they applied this to the robustness experiments, they found that the model achieved even higher accuracy on those corrupted prefixes when using lower temperatures. This suggests that the model isn't just randomly fixing errors, it's actually using its understanding of the CFG to guide its corrections, making it more robust to all that noise and inconsistency in the input.
That's really impressive. So we've gone from the model demonstrating this remarkable accuracy in learning CFGs to uncovering potential mechanisms behind this learning. And now we're seeing its ability to handle real-world imperfections in data. What are the bigger implications of these findings? Where do they lead us in the grand scheme of language models and AI?
That's a great question, and it's something we'll delve into in our next deep dive.
We've certainly covered a lot of ground in this deep dive. We've really explored the fascinating ways language models grapple with those complexities of context-free grammars.
We have. From the model's remarkable accuracy in generating grammatically correct sentences to the intriguing possibility of dynamic programming-like mechanisms, and of course, its impressive robustness in handling corrupted data.
So where do these findings lead us? What are the broader implications, especially in the grand scheme of language models and artificial intelligence as a whole?
This paper really presents a compelling argument for going beyond just evaluating language models based solely on their outputs. It's about delving deeper into their inner workings. Understanding how these models learn and represent complex structures like CFGs could really unlock significant advancements in their capabilities.
It's like shifting our focus from simply admiring the final product to actually understanding the intricate craftsmanship that went into making it.
Exactly. And this shift in focus, well, it could pave the way for developing more sophisticated and adaptable language models that can tackle an even wider array of tasks. Think machine translation, code generation, even creative writing. The possibilities are really quite vast.
The paper's findings on robust pre-training are particularly relevant to real-world applications. It's pretty valuable to know that even a small amount of intentionally corrupted data during training can significantly improve a model's ability to handle imperfections later on.
Absolutely, and that has huge implications for developing language models that can operate effectively in those messy real-world scenarios where, let's face it, data is rarely clean and perfectly structured.
And that potential connection to dynamic programming is super intriguing. Could this lead to the development of more efficient, more effective training algorithms?
It's certainly an exciting avenue for future research. By leveraging this insight, we might be able to optimize our training procedures. That could enhance the model's ability to learn these complex grammatical structures. We might even see faster convergence and better generalization.
Imagine the possibilities. If we could really understand and harness the model's internal grammar checker, we could create models that are incredibly resilient to noisy data. That would mean more reliable performance in all sorts of real-world applications.
And it's not just about performance and robustness. I think this research also has profound implications for the interpretability of language models. If we can grasp the mechanisms behind their learning, we can start to shed light on how they represent knowledge and make decisions.
That's a crucial piece of the puzzle when it comes to building trust and confidence in AI systems. If we can understand how they work, we can better ensure they're operating as intended. We can avoid those unintended biases or behaviors.
This paper really does open our eyes to the incredible potential of language models. It goes way beyond simply generating human-like text. It's about understanding how these models learn, represent knowledge, and interact with the world.
It seems we're truly at the dawn of a new era in artificial intelligence. We're moving beyond simply observing those impressive outputs. Now we're delving deeper into the intricate mechanisms that drive these powerful models.
And as we unravel these mysteries, we unlock the true potential of language models. And this potential goes beyond revolutionizing communication. It extends to how we learn, solve problems, and even interact with the world around us.
Well, thank you for joining us on this deep dive into the world of language models. It's been a fascinating journey, and we hope you've gained some valuable insights from our exploration.
Until next time, keep exploring, keep learning, and keep pushing the boundaries of what's possible with artificial intelligence. 2388C